Good morning, boys and girls. Here's just a short video on the practice problems from lesson 11 in reference to polygons. Much of today's lesson is, types of definitions and what polygons are and what they're not. So we're going to start here with number one. Select all the polygons. I've been using a lot of red lately, so maybe I'll go to blue. So A is, in fact, a polygon, right? Made up of all straight line segments. It's an enclosed figure. It has sides. We're good. No, or I should say it has no curved edges, made up of all straight line segments, and it's an enclosed figure. So that's a polygon. B, not so much, because it has a curved segment to it, right? That curved segment, by definition, it's not a polygon. C, absolutely. D, no, because it's not an enclosed figure. E, no, because it has curves and segments to it. And F would not be a polygon because it is a three-dimensional figure, or an attempt at drawing a three-dimensional figure from in two dimensions, which isn't easy. Okay, mark each vertex with a large dot. How many edges and vertices does this polygon have? So the vertexes are basically meeting points of all the line segments in a shape. A vertex is all the line areas where all the line segments meet. So let's count these out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 vertices and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Where did I start? Let's do this in a different color. I'll start here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 edges. 12 vertices, 12 edges. Number 3, find the area of this trapezoid. Explain or show your reasoning. Well, this trapezoid, I would probably take this segment and rotate it upside down here. Let me just make sure it's the same size. 1, 2, 3, 1, 2, 1, 2, 1, 2, 3. So it is. I would probably do that. Chunk that out like we did with the parallelograms. And then, of course, this part is gone. And now what do I have? I have 1, 2, 3, 4, 5, 6. It's just a 6 by 3 rectangle. So the area is 18 units squared. Now I could have done it another way. Naturally, there's always another way, isn't there? I could have done it another way. I could have broken it up into a smaller rectangle and two triangles. So the smaller rectangle here is a 4 by 3, so that area would be 12. And these two together make a 2 by 3 rectangle, which would have an area of 6. And then I would just add those together. Number 4. Lynn and Andre used different methods to find the area of a regular hexagon with 6-inch sides. Lynn decomposed the hexagon into 6 identical triangles. Good idea. Andre decomposed the hexagon into a rectangle and 2 triangles. Also a good idea. Find the area of the hexagon using each person's method. Show your reasoning. Okay, so let's see. We know that 6-inch sides. So that's 6 inches, that's 6 inches. That must form a right angle. Notice the distance from here to here is 10.4, boys and girls. So that tells us the height of this is 5.2. So therefore, the dimensions of each of these triangles is a base of 6, and a height of 5.2. Base of 6, height of 5.2. So 6 times 5 is 30, and 6 times 0.2 is 1.2. We'll talk more about that computation part there another time. 31.2 for each triangle, and of course there are 6 of them. Oh wait, I forgot to take half, right? 31.2 for the area divided by 2, of course. Oh, I could just multiply it by 3. Yeah, I'll do that. So that's 15. That's 0.6. Add those together. 15.6 for each one times 6. So 6 times 15 is 90. 6 times 6 is 3.6. So I come up with this method, I come up with 93.6 inches squared. Okay, so this is a rectangle, this part in the middle, which is a 6-inch by 10.4 inch rectangle. You need to use a calculator for these computation parts. I don't mind that, boys and girls, because we haven't really talked about computation strategies at this point. I'm just sharing a couple with me. I know I could set this up as a conventional algorithm, but I'd like to do these like this. 6 times 10 is 60. 6 times 0.4, well, 6 times 4 is 24, and there's a decimal there, right? So it's 2.4. So that's 62.4 for that piece, And then each of these triangles has a base of 10.4 and a height of do we know? Let's see, what can we do with those triangles? We could cut off that piece, right? We could do that. And if we did that, what's the distance? All right, let's think about this for a second. 2 triangles, 6-inch side, 6-inch side. Distance from here to here is 10.4. I'm looking for the distance from here to here, and I don't see where they're giving it to us, so we have to do that in a different way. So very interesting, boys and girls. I actually had to look this up myself because I was trying to use, the math that we've covered and that we know in order to solve this, and very clever. So the solution of finding that distance that I was looking for right there. So we've already found the area for this, right? That's the 62.4. And then the solution here is that they told us in the prelim that each of these sides of these triangles are 6 inches. And once you know that each of these sides are 6 inches, you know that the distance from here to here is 12. So that means this distance, of course, of 6 can be subtracted away from 12, which means this segment and this segment, when added together, is 6, which means the height of these two triangles is each 3. So it is a 10.4 as the base, 10.4, and 3 as the height. So this is one of those triangles in which I'm not going to divide it by 2, and here's why. I'm finding the area of 2 of them. So normally what would I do? Base times height divided by 2, and in this case I'm not going to do that because I'm just going to multiply these together. So 3 times 10, of course, is 30. 3 times 4 is 12, plus the decimal part, right? 3 times 4 is 12, so 3 times 0.4 is 1.2. So that's 31.2. Let's see if we come up with the same thing on this method. 0.4 and 0.2 is 0.6. 2 plus 1 is 3. And 6 plus 3 is 9. So we come up with the same ones. This is a very interesting problem. We will no doubt talk about this a little bit in class, and hopefully it didn't give you fits when you were doing it. Nicely done. Way to hang in there, boys and girls, and have a great afternoon.